Also during this time, this guy Arthur Compton discovered something pretty cool. He would sit electrons, have them just sitting there, and he'd shoot X-rays at them just to see what would happen. Maybe would the electron get excited or what? And so what happens is this X-ray would come in, and then it would go pop, and this electron would go this way, and this electron would go that way. So let's watch that again. So the X-ray comes in, something happens here, and you get this happening. This actually would change into a slightly longer wavelength electron or X-ray. So this X-ray now has less energy than the other one, but this electron would go zinging off in this, it was sitting here and then would go zinging off in this direction. Let's go back to a couple chapters ago. Momentum initial equals momentum final. Before this electron got hit, it's not moving, so it has no momentum. So the momentum of the electron is 0. The X-ray comes in, it's a wave. Waves have no momentum. So then afterwards, bang, it would hit. This would turn into this one, come off at some angle. But now the X-ray has no, but now the electron now has some. Where did that come from? Oh, maybe the conservation of momentum doesn't hold. This is not true. This thing we've been learning for hundreds of years is all of a sudden wrong, which was discussed. But maybe we don't understand this very well. Maybe this photon, maybe this chunk of light that's coming in, maybe we don't understand momentum. So let's take a look at it a little bit. So we know its energy. Its energy is HF. Its momentum, that's a little bit trickier to understand. So what we decided to do was swap these over and see if we can get rid of some mass. Or the mass doesn't exist here, so we have to try to figure. So P equals mv as we thought, and E equals HF, but it also equals this mc squared, and I think I like that one better. So let's look at the ratio of the momentum over the energy. So that turns into mv over mc squared. Oh, look, the m drops out. That's nice. V over c squared. How fast is this thing moving? This thing's moving at c, so I have c over c squared. So one of the c's go away. So the ratio of this electron's momentum over energy is just 1 over c. This is really handy. So now let's keep going. P times c equals the energy. Let's move this, get P by itself. I didn't like doing that. Let's swap that around. So now P equals the energy over C. The energy is also HF. So the momentum becomes HF over C. Oh, nice. This has a frequency. We can figure out what the momentum is from the frequency, but also V equals F lambda. And if we move this around, C equals F lambda. And so F is equal to, let me do some math here, F equals C over lambda. So then when I plug this back in over here, P equals HC over C lambda. The C's cancel out. The momentum is H over lambda. So now we have 2 equations for momentum. Momentum is this deeper idea than just mass times velocity. Waves can also have some sort of momentum, provided they have a wavelength, of course. So now waves have momentum as well. The guy who figured this out was a guy named de Broglie. So this is called the de Broglie wavelength. Oh, whoops. That's the next lesson.